My guest again today is Joseph Fournier.
Last year in May, I gave a similar presentation. And today, it's sort of like, in my mind, it's sort of like part two. The first presentation I gave had a very strong focus on Pacific Ocean atmosphere processes, also known as Walker circulation, and how that relates to data that is specific to the tropospheric growth rate, isotopic carbon-13 data. This year, I am focusing on how Walker circulation and Pacific processes relate to changes in what's called the other greenhouse effect. The title here, there is not one greenhouse effect, there are two. That is, for people who are familiar with the literature, that is not a surprise thing to hear said. But for those who are not familiar with the literature, that it's actually quite puzzling to hear that statement, because you only ever hear about one. So that's the whole point of this. At least the first half, 3/4 of this presentation is going to be how Walker circulation dynamics controls the Earth's largest greenhouse effect. So these two pictures here I think are just, they're powerful. I want you to, these are called deeply convective anvil clouds that you find over regions where there's a tremendous amount of evapotranspiration or evaporation, and they go way up in the atmosphere. So this is an example of the largest greenhouse effect, which is focus of the first two parts of this presentation today. So I am no expert in atmospheric physics. I have an above average understanding because, like many with obsessive compulsive disorders and cites, I love to study things. And so I'm not going to dive into cloud physics. I'm just going to, some basic nomenclature and some basic ideas. So the starting point for the presentation is just a basic reminder for what most people know above the age of 5. And that is, there are different types of clouds. You'll see them during the day, you'll see them during different times of the year, and as a function of geography. So this picture here I've got is just a basic reminder that there are high elevation clouds and low elevation clouds. And they all have different radiative properties. So when we talk about radiative property, we mean like how much incoming sunshine is being reflected off their tops back to space, as well how much outgoing heat or long-wave radiation, OLR, but outgoing long-wave radiation, is reflected back to Earth. A lot of us are familiar with the idea that an overcast night is a warmer night versus a clear sky night. So in the literature and in atmospheric physics, we talk about net cloud radiative forcing, CRF. Net is just the sum total of both long wave and shortwave. So RSW is your reflected shortwave radiation. So you'll see that on the right-hand side, net CRF equals LW CRF plus RSW CRF. Typically, the RSW is a negative quantity, and the LW radiative forcing is a positive quantity. If a cloud has both these properties where they're reflecting incoming radiation from the sun and back reflecting outgoing heat from the Earth's surface, it's the balance between the two which will determine whether or not a cloud has a net negative cooling effect on the surface or a net negative or net positive warming of the surface. So those are just some of the terminologies. On a global average basis, net CRF is less than 0, meaning clouds are a cooling agent. But net is an important term because all clouds, more or less, have also a warming effect, i.e. it's insulation to outgoing radiation. We call that also a greenhouse effect. So here's just an image that helps convey some of these ideas, right? So I just generated this meme for social media, and I found it helps convey these complex ideas very clearly for people, and it's gone over quite well. So clouds on average have both a cooling effect and a greenhouse effect. You can see here trapped, the image shows where the heat is being trapped with those red arrows. Emitted heat is where there's gaps in the cloud, and heat from the radiated from the Earth's surface is able to escape out through the top of the atmosphere. You can see absorbed sunshine, and that's what actually hits the surface and warms the surface. Reflected sunshine is shown there as well. So there's a reference I've got there. If it doesn't come clear in the presentation, you can view this slide subsequent and you can see the reference. But this reference that I got here, this is from a book. It says that a 1% reduction in the Earth's reflectivity from decreasing cloud coverage causes an extra 2.1 watts per square meter of heat to escape from the lower atmosphere and 3.2 watts more sunshine to be absorbed by the surface. So conversely, when cloud cover increases, those go into reverse. So declining cloud cover is net positive warming, right? Because 3 was bigger than 2, right? So another comment, another quote I've got here from the literature is that 1% reduction in planetary albedo. Planetary albedo is not just the atmosphere; it's glaciers, land, ocean. It's the entire reflectivity of the Earth is albedo. But a 1% reduction in planetary albedo, or approximately 3 to 4% reduction in the average cloud coverage, has the same warming effect, theoretically, as a doubling of CO2. All right, so that's also from the literature. You can even find that in IPCC documents. So this is not unconventional. This is just not well advertised ideas. So here's an example. Okay, here's an example of this reference about albedo and its equivalent to a doubling of CO2 effect. Here, that the quote I've got down there, and that's from the IPCC 2007. It's from their one of their lead authors actually made this quote, and I'm just including it here. We've got HADCRET 3, global surface air temperature anomaly, for the last couple decades of the 20th century, plus the first decade or so of the 21st, compared to the tropical cloud cover. I think it's between 10 north and 10 degrees south. And that data is from a satellite that we refer to as ISCP. They name it's one of the earlier generations of satellites that was used in quantifying cloud dynamics, statistics across the Earth's surface. So this is the first example now of geographic specificity to date. All the ideas that I've been talking about are referenced relative to a global average. Next slide. So a very familiar name in climatology is Kevin Trendberth. This is a 2009 study that the title, Global Warming Due to Increased Absorbed Solar Radiation. So in 2009, he's referencing data from the last couple of decades of the 20th century. And the abstract here, I've got key elements from it that I just wanted to bring to bear as during the introduction here. And that is basically Kevin is saying that decreasing cloud cover during the last 2 decades of the 20th century, where we saw a very steep rise in warming on an average basis, on a regional basis, he says it's due largely to decreasing cloud cover and increasing sunshine hours, or the energy of solar radiation being absorbed by the Earth's surface. Also, what he says here is very important. I've highlighted and read down over at the bottom. The middle, it says the big part of this warming effect due to decreasing clouds is it acts to offset the radiative forcing or the CO2 greenhouse effect, right? So if clouds decrease, more heat escapes from the Earth's surface. But if in the background, the other greenhouse effect is slowly increasing, well, if clouds, which they are a stronger radiative warming effect from in terms of outgoing heat, if that is dumping heat faster than the radiative forcing or greenhouse effect for CO2 is rising, then it's basically offsetting. And it's an argument now of which one is larger. We'll go into that. So this is a good point to just emphasize. Again, what I'm talking about has been known now for decades. It's just not talked about much. So here's an example. So this is a very important historical study that was done using first generation satellite technology. So this author has been referenced a gazillion times, and it was one of the very first global assessments of forcing of effect from like the greenhouse effect, Longwave, radiation trapping effect of clouds as a function of geography, as well as shortwave reflectivity as a function of various types of clouds and across the Earth's surface. So the false color imagery, the bar on the bottom shows that this is specific to the long wave radiation forcing, or CLW, in this paper. It shows that there are key locations along the equatorial latitudes or tropical latitudes. For example, over Indonesia, Papua New Guinea, you see some very strong radiative warming effects from the convective clouds that are there, the deeply convective clouds over these tropical regions. You see it as well over the tropical South America, tropical Africa. And then likewise, the lighter blue shows that whatever clouds are there that are not very effective in blocking outgoing long wave radiation. But this study here, this is the highlights that I want to remind people of here from this work is this first generation of satellite data reveal that the CLW on average for all the Earth and all the different types of clouds on average, the radiative warming effect or the greenhouse effect of clouds is 8.5 times larger than would be caused by a doubling of CO2 effect. Okay, so that's extremely important to emphasize. The clouds, the greenhouse effect produced by clouds absolutely dwarfs even a doubling of the CO2 concentration. Whatever greenhouse gas effect that produces, it's dwarfed by clouds. And furthermore, the studies would argue that you would have to increase the concentration of tropospheric CO2 by 100-fold to produce an equivalent greenhouse effect to what is already there naturally by clouds. So down here, I've just included from this study some of the CLW values for various types of clouds. And you can see that the largest is deeply convective clouds. These are the ones that I showed you on the cover slide. It's these massive anvil structures that look like a big atom bomb going off. Those are the most powerful greenhouse effect clouds. And as you go down into closer to the Earth's surface, there the greenhouse effect decreases. So here is a slide that I prepared using recent literature data that compares cloud greenhouse effect changes versus composition, like CO2 composition change related effects on the other greenhouse effect. So in the recent study here, Hans Rudolf Dubow et al., 2021, here they've got total average on a global basis change in cloud percent It's blue versus outgoing long wave radiation in orange. And you see right around 2000, there was a step change, right? There was a very large drop, a couple percentage points over a period of just a few years. And you see OLR heat is escaping much more effectively. And so that is a confirmation of everything I've been talking about. Clouds, trap heat, remove those clouds at a certain amount, and heat will escape so much easier. So on an average, if you draw a linear line through there, it's about 1 watt per square meter per decade. The Feldman et al. Nature 2015 study is a measurement of how the other greenhouse effect is increasing from 2000 to 2010. And this study found that it was about 0.2 watts per square meter per decade. So the clouds are decreasing, the greenhouse effect for clouds is decreasing 5 times faster than the greenhouse effect from rising CO2 is increasing. So this speaks to what Kevin Trendberth was talking about, the offsetting potential of reducing clouds, what that has, the effect that that offset has on rising CO2 concentrations. In other words, the greenhouse effect from rising CO2, according to these two data sets, suggests that it doesn't even exist. It's being offset entirely by a factor of 5 by decreasing clouds. So geography matters. It's going to be a theme here that I want to just hammer home. Global averages have limited value. Very, very few things change geographically, coherently on planet Earth. There are regimes. There are geographic processes that, like the Pacific process, the Arctic, the Antarctic. You see where I'm going with this. This is a reanalysis product from the Japan Meteorological Agency. It's a 25 years of reanalysis data that they've produced the planet Earth, and it's the what's called global column integrated heating. Note the axis on the right-hand side, the units are watts per square meter from positive all the way down to negative. So you see that the Western Pacific is the region where it has the most positive integrated heating on the planet. Conversely, on the opposite side of the Pacific is where you have some of the most intense negative cooling. It's that contrast between cold and hot in the Pacific that drives Walker circulation. The trade winds upwelling of deep cold water on the east side, the deeply convective rising air masses along the west-hand side, and it just rotates over. I'll show you those pictures in the subsequent slides just to help build a better picture. So my focus, and you'll find the focus of this presentation is going to be increasingly on the Western Pacific warm current. But it's, as you can see, it's the most red and the largest red zone on planet Earth. Notice as well the red line corresponding to the where the equatorial latitudes are. Equatorial latitude, that's where the Pacific trade winds dominate. So the trade winds come from the east and they move west. And as they move west, they push warm water into the warm pool. The warm pool dynamically has been studied and documented a lot over the 20th century. This little slide here shows its significance from a Western North American or Western Canadian perspective. Climate processes in the Pacific, particularly the lower latitudes, have a marked effect on climate, particularly winter climate. I'll probably send you a slide deck sometime later this year where I'll dive into winter weather trends, climate trends relative to this part of the Pacific. So here in this slide, we've got two time series. The top one is the area, the anomaly of the Western Pacific warm pool. You see the average is defined as 12 million square kilometers. This is an anomaly plot where the y-axis is percent deviation from average, right? So red means it's the pool is increasing in size. Blue means it's shrinking in size. Down below is the sea surface temperature anomaly plot, and they're complementary. By definition, the warm pool is defined by the area where sea surface temperatures are above 28 Celsius. So that there's a line, and that line and that area contained within that perimeter is changing dynamically as a function of time of year, month of year. On an interannual basis is changing, and on a multidecadal basis it's changing. It's always changing. So this is you notice this picture here I've got, it's from southern Alberta in 1948-49. It was a period of some of the most intense winters on record, in at least the 20th century. Those poor cows there, a lot of them would, it was quite common back in those days where cows would suffocate, buried in drifts during some of the winter storms that we had. One of the worst ones in Canadian history was in 1967, and it's estimated about 10,000 cows died, suffocated in massive snowdrifts that happened when the Pacific was going through one of these negative excursions. So it's this dynamics is here is basically the black line is like a 5-year rolling average. It's not like it helps you see the decadal longer term processes of change. Most of the data that we're going to move into in the next slides is going to be more 12-month rolling average. So focuses on the timescales of ENSO, the El Nino Southern Oscillation, which is an interannual change. So this cross-section is really helpful when we're studying Walker circulation dynamics at the timescales of interannual changes, the timescales of ENSO. The top one is when ENSO is neutral or La Niña conditions. That's when, as you can see, over the Pacific Ocean, you'll see that the prevailing tropical or equatorial wind direction is from the east to the west. We call it Easterlies, also called the trade winds. Note that when we've got ENSO neutral or La Niña conditions, the deeply convective clouds are positioned over the western Pacific warm pool, over Indonesia, Papua New Guinea, over subtropical, tropical Africa, and South America. Just like that CLW plot that I showed earlier in terms of where the most powerful cloud greenhouse effect is of the planet. It's over these cloud formations. So when we're in an ENSO neutral state, where those clouds are, that's where the strongest cloud greenhouse effect is. Now, when El Nino conditions kick into high gear, particularly strong El Ninos, you'll see in the diagram in the bottom, the easterlies change direction. They don't just slow down, they will actually change direction. And when they do, that deeply convecting cloud formation over the western Pacific warm pool moves towards the Central Pacific region. Likewise, over South America and Africa and Indonesia, they almost disappear. And it's because of the changing atmospheric circulation patterns that are telekinetically coupled across the global tropics. The dominant process is what occurs over the Pacific, and the Indian and Atlantic follow. I hope that is a good enough explanation for people out there who are more of an expert than I. Next slide, please, Tarwin. So those clouds, when they are particularly over the Western Pacific warm pool, the trade winds, as I've alluded to, are pushing warm surface water westward into the warm pool. Now, I've got two sets of diagrams here. One is this false color image showing the dynamics of the subsurface thermal haline across the Pacific subtropic region. Red meaning warm water. You see in the top right-hand one where it's really red to the west. That's when we're in ENSO neutral or La Niña conditions. The thermal haline has been charged up with hot water from the Easterlies. Now, when you see the next slide down, next image, where it's discharging, that corresponds to where the Easterlies suddenly collapse or reverse to a wet prevailing westerly condition. And that warm pool in the west sloshes to the east through the Central Pacific and into the Eastern Pacific region. Now, the bottom of it says it's fully discharged. Well, discharge means that heat's been dissipated and it's moved not just eastward, but towards higher latitudes in either hemisphere. So it's like a big thermal capacitor. When it's in a neutral La Niña state, the Pacific warm pool is charging out the thermal energy. And those easterly winds are slamming that, pinning that body of water underneath that large greenhouse effect, limiting the release of heat through the top of the atmosphere, because that deeply convective greenhouse is limiting ventilation of heat, thermal energy stored in that water body. Now, the time series that I've attached for the literature here basically shows the temporal correlation between the warm water volume in the west, in the warm pool region, which is red. So you'll see it's an anomaly plot, so it's a deviation from average for both the warm water volume in the west, as well as the Niño 3 sea surface temperature indice, which is specific to the Central Pacific region. So you note how towards the left around the early 1981, 1982, the warm water volume starts to rise. And as it starts to rise and peak, well, it slows and then suddenly reverses. When it reverses, notice that the Niño 3 region in the Central Pacific suddenly experiences a surge, an increase in sea surface temperature. And that's because that warm water volume is sloshing eastward. And with it, it's pouring that deeply convective cloud cover that moves with the thermal haline displacement eastward. Its greenhouse effect above it moves eastward with it. And that is, in those two processes is why the Niño 3 region and the other Central and Eastern Pacific regions see a rise in sea surface temperature at the timescales of ENSO dynamics, because that thermal haline is moving eastward during the El Niños, and that deeply convective cloud cover, that greenhouse effect, is moving eastward with it, trapping that heat. Though it's important to emphasize the scale of this volume of warm water. I've got the notes here. The variance is anywhere between 100,000 to 600,000 cubic kilometers of plus 28 surface temperature waters are sloshing back and forth across the Pacific. So it's a huge number. It's a tremendous amount of sensible heat and latent heat that's involved in this back and forth motion. I hope that is a sufficient explanation. So I've talked about the role that the trade winds have in moving surface water from the eastern and central Pacific westward into the warm plate. But this plot here is a monthly mean sea level anomaly plot over the equatorial warm plate. The vertical axis should be labeled, my apologies, it's in meters. So a positive 0.2 means on average this region has increased by 0.2 meters in elevation. A negative 0.3, get the drift. It is dropped by 0.3 of a meter. The sudden negative values that you see, those are El Nino events. And the deeper negative it goes, the stronger or the longer the El Nino persists. So when you think of the wind shears that are pushing that equatorial subtropical water westward into the warm pool during neutral and La Nina conditions, it's hitting. The reason why the elevation is rising because it's hitting the ASEAN nation shorelines, and it can't. All that surface water, all those currents, they can't leak through into the Indian Ocean fast enough because of the landmass is blocking. So the water actually piles up. So that sloshing effect that you saw in the previous slide, the thermohaline migration across the Pacific during El Ninos, is basically it's releasing this gravitational potential energy that was built up, and it's just flowing downhill. And then when the ENSO neutral or Niña conditions begin again after an El Nino, it quickly recharges. So a lot of data here, but this is complementary to everything I've said. Just to show, number one, that what I'm talking about is just this long-held knowledge within oceanography and atmospheric physics. This 2007 study, the ENSO surface long-wave radiation forcing over the tropical Pacific, is confirming everything that I'm talking about. In this top left-hand plot, the colors correspond to basically an anomaly, negative downwave long-wave radiation, DLW. That's basically the cloud greenhouse effect. Okay, so in this plot that I show on the top left-hand side, that's during an El Nino, and you'll see that during an El Nino, just as I've talked about, the central region, the Niño region, Niño 3.4, Niño 3, Niño 1 and 2, they become, you see a much stronger growth in the down DLW, the greenhouse effect over this region, because those deeply convective clouds that's where they've moved. The negative values that you see over in the Western Pacific warm pool, it means that region is now ventilating all that excess heat that was stored there. The greenhouse effect from that large convective cloud formation, it's gone, and now it's just releasing heat like crazy. The plot down below is from the same study. This is DLR versus Niño 3.4 index. So you'll see it's a linear slope, very good R fit 0.9. It confirms that as the Niño region sea surface temperature rises, the greenhouse effect over that part of the Pacific rises as well. It's a linear relationship, and it's a function of the the area coverage of these deeply convective clouds. The warmer it gets, the stronger that convective cloud cover is. And if you look at the time series that I've got right here from NOAA on the right-hand side, OLR over the Central Pacific versus ENSO time series from 1974 to April 2024, the red shows that OLR over that part, the Niño region, decreases when an El Nino event is occurring. Likewise, it ventilates heat more effectively during La Niñas. And that's, again, it's just a function of where those clouds are, those deeply convective clouds over the tropics. They're sloshed back and forth. And that's what we're seeing when we're looking at this OLR data, which is outgoing and downwelling DLR or DLW. That's the radiation going down, reflected. That's the greenhouse effect. So I hope that explanation helps. That's some really good classic literature data. So there's another study here. Not going to dive into it too much. It's pretty complex, but it's a seminal study. It comes up commonly, and this study was specific to cloud radiative forcing dynamics over the Pacific warm pool as a function of ENSO. And the N value that you see is just a ratio of shortwave cloud radiative forcing divided by the longwave cloud radiative forcing. Typically speaking, as you know, we've got 3 different years there: 1985, 1989, and then 1998. 1998 was a very powerful, one of the largest in the last 50 years, Niño event. And you'll see there that the ratio, that N value rises. And that's the reason why is, well, it's because those clouds, those deeply convective clouds have moved eastward. And in so doing, the LW, the cloud radiative forcing some long range radiation, the denominator has decreased while the numerator has increased. Right? The numerator is sunshine. Because those clouds have moved eastward, more sunshine is getting into the warm pool, and the regional greenhouse effect decreased. So at N value, it moves positively. It reflects those 2 inverse processes. So it's really just emphasizing the structural changes that are occurring during El Nino versus not El Nino conditions in the Western Pacific warm pool. Such that during El Nino events, the Western Pacific warm pool is releasing heat through the top of the atmosphere much more effectively, but also absorbing more incoming solar radiation because there's less cloud top reflectivity. So here's just an average. This is a study done 2009, basically this is the last 20 years of the 20th century. And this is like a decadal average. The axis, the units of it is cloud covered percentage per change in temperature, sea surface temperature. So it's a ratio. And the focus is over in the Pacific region. And during the last 20 years of the 20th century, there was more El Ninos than there were La Niñas. And so as a result, on a 10-year, 20-year average basis, you see the Western Pacific warm pool saw a reduction in cloud cover. Likewise, we see that on the eastern side. As sea surface temperatures rose, those regions saw less clouds. So you're absorbing more sunshine and ventilating heat more effectively through the top of the atmosphere. The opposite is found in the Central Pacific region. So on an average basis, those deeply convective clouds, the warm pool greenhouse effect, has displaced on average more towards El Ninos. So I'm really beating this one to death, really trying to help people see from the literature and the history of how clouds change, particularly the greenhouse clouds change as a function of changes in the surface temperature, which is driven by things like ENSO or longer time scales, which is like the Pacific Decadal oscillation or the interdecadal Pacific oscillation. Those are longer term indices of change. So now data that I collated together. So got data here from UAH data, University of Huntsville, Albedo. This is the microwave sounding of the lower troposphere satellite measurements of the tropospheric air temperature of global average. So it's the global average air temperature anomaly, GAT anomaly, as we often say, versus satellite measurements of outgoing long wave radiation relative to 2000 and relative to the top of the atmosphere. So OLR is outgoing, right? So just keep that in mind. It's been 12-month rolling average data. So it's really because of that time scale of averaging, you're able to see with better clarity the time scales of ENSO dynamics or Walker circulation, right? The R squared between these two plots is shown. It's 0.83. So it's when I first saw this data set, I was like, because I'm so obsessed about, specific processes, I was like, wow, that is a remarkably correlated relationship. When I first saw the OLR data that I got from my friend Rodney McInnes, he passed this over to me a few months ago. I was like, I gotta plot that against the GAT anomaly. So both are global average changes, but they are showing very, very, very clear Walker circulation dynamics. The other thing here is showing is that on most timescales, particularly around larger ENSO events, like El Nino events, particularly, you see OLR starts to rise ahead of the GAT anomaly. Okay, so thinking back of everything I've just talked about in terms of like the temporal sequence between changes in those, the location of those clouds, those deeply convective clouds over the warm pool, and how the warm pool volume, the thermal haline in that region, how it begins to move eastward before the Niño central region of the Pacific starts to warm. But think of that temporal relationship, the lead and the lag. We're seeing a very similar lead and lag here between OLR, global OLR, and the GAT anomaly. And so it's really helps me appreciate, number one, regional effects are dominating the global average. So what is the global average? Well, it's definitely not speaking of a highly coherent, geographically coherent process, right? If you go back up, can you just go back up to where that the Japanese meteorological global integrated heat column plot is? Just scroll up if you can. A few more up. There we go. Back down that big map that shows the heat across the Earth's surface. That one works too. This is the cloud forcing, long wave radiation cloud forcing plot. It shows very clearly there's a lack of geographic coherency. So when we talk about global average greenhouse effect from clouds, you can see it's not coherent. It's local. So you can go back now. Just wanted to remind people of the of this reoccurring theme in global averages don't tell you anything about geography. And so you always have to be very, very careful when interpreting global average data. Next slide, please. So just to confirm, to test the idea that the changes that we're seeing in the global OLR is connected to changes in the deeply convective clouds, or that very large long wave radiation forcing over the tropical regions. I wanted to compare his OLR against the Pacific trade winds speed anomaly. An anomaly is a good way to represent trade wind data. It's inverted positively. So when you see a positively trending anomaly for trade wind, it means the easterlies are decelerating. I've got that on that labeling on the left-hand y-axis. When it's going negative, it means the easterlies are accelerating. So accelerating easterlies is La Niña conditions. Decelerating easterlies is El Niño conditions. And no surprise here, you see a remarkable relationship, a very strongly correlated relationship between the trade winds and the global average OLR. The trade winds, if you look at it on a percentage of how much area of the Earth's surface is where you see the trade winds localized, only 4% of the Earth's surface is where the trade winds exist. But this tiny little speck of ocean is here being shown to have a very, very strong relationship with the global average outgoing heat to space. So, it's a bit redundant, but it's important to be redundant. I'm just showing the GAT anomaly from UAH global tropical air temperature anomaly. This is the tropical one now, so like 30 north to 30 south, all the way around the world, showing that the air temperature, the deviation from average across the tropics is a function of Walker circulation dynamics. So it's, two things equal to the same thing are equal to each other. They're all speaking of the same process at work. OLR, GAT, or tropical air temperature anomaly, they're the same. They're just averages. They all show the same relationship to trade winds. And trade winds is the proxy for Walker circulation. Okay? So I think we can move on. That point is made pretty good. Now, I've been talking about greenhouse effects. So predominant variable we think about is outgoing long wave radiation. But as the introduction, we emphasize clouds have both a warming effect and a cooling effect, right? The greenhouse effect is this warming effect because it limits outgoing heat. They also they're the control knob on how much sunshine is absorbed by the surface. So it's logical to now look at absorbed shortwave radiation data, ASR, relative to 2000. So that's a change. It's not an anomaly, similar philosophically to an anomaly, but it's just a difference relative to like January 1st of 2000. Get the vertical axis on the left is the ASR, and the vertical axis on the right is the gas anomaly. Both negative and positive, that because it's an anomaly. You'll see that we've got an R-square about 0.46. Pretty good, but not as good as OLR. So There is some strong indicators in here in this global average ASR that, ENSO dynamics are a factor, a major factor, particularly when we look at the time series from 2015 to present. There's some pretty significant bumps on there, and dips and rises that have a El Nino La Nina like signature, but it's nothing near as close as we saw with the global OLR. Now, I wanted to bring this one from the literature. This is a 2024 study. The focus was on, the focus is the title, is let's look at how the reflectivity of planet Earth changed during the early stages of the 2023, or during the 2023 El Nino versus the prior 10-year average. So I've just got the satellite measurements of low cloud cover. This is not total, this is just low cloud cover. Okay, this is the most low elevation clouds, like marine stratiform, stratus cloud formations. They are the most reflective of incoming radiation. So in terms of reflectivity or albedo, the author is focusing on low elevation clouds. High elevation clouds are not as reflective, surprisingly not, compared to low elevation clouds. So the blue means cloud cover of percent per decade is increasing, negative. And the red means the 10-year average is decreasing. So in the left-hand map, the 10-year average shows Eastern Pacific saw a rise in low elevation, like marine stratiform clouds. And that's because during the last 10 years, the region experienced one of the most intense La Nina events in recorded history. It was a La Nina for 3 years back to back. So those Easterlies were pumping up deep cold water to the surface. Walker circulation was intense, and the downwelling of the atmosphere on the surface in the Eastern Pacific was creating dense coverage of marine stratiform clouds. And that's what we saw there. And that corresponds to a negative interdecadal Pacific oscillation. Likewise, you look at the Atlantic region is the opposite. From the tropics to mid-latitude regions, we saw a very significant reduction of upwards of 6-8% of clouds, low-lying marine stratiform clouds over the Atlantic region. And that's corresponding to a positive AMO condition, which has been prevailing during the same period of time. Like the Pacific was in a negative IPO state. We compare that to the annual average over 2023. No surprising, when we had an intense El Nino event in 2023, that Pacific cold zone region in the east disappeared because Walker circulation collapsed, marine stratiform clouds disappeared, and you saw some reduction in the marine stratiform clouds over the Pacific and Atlantic subtropical regions. And it just shows how those two Niño regions are teleconnected to each other. So here's ASR versus OLR. I love this plot because it shows the great hiatus so clearly. There's like no real trend during the first 15 years of the 21st century. But then something changed around 2014, 2015, that powerful Central Pacific El Nino, and then followed by two other El Ninos, basically back to back. The ASR, you're seeing global average absorbed sunshine levels are rising significantly over a 2-year period. OLR is not rising as fast as ASR is rising. So that's super important to emphasize. When ASR leads, grows faster than OLR, well, the climate is warming, right? So more energy is being absorbed by sunshine, then is faster than heat is able to release it through the top atmosphere. Notice there is around 2020 to 2024, 2004, when the OLR went through its 3-year dip there. That was when that Western Pacific warm pool, that large greenhouse effect, moved westward. OLR took a big dip. ASR did not follow it very clearly. In fact, it peaks even before it peaks. The ASR peaks there around 2023, even before OLR does. And that's one of the limitations that we find when we look at global averages. It doesn't tell you where. You know, statistically, geographically, which region of the world is contributing to that ASR, global average ASR trend. It's clearly differing on some features than the OLR. The OLR is showing a much more consistent ENSO feature that's not reflected as perfectly in the ASR. Moving to the next slide, I'm just now going to show the difference between ASR and OLR. That's your Earth energy imbalance relative to 2000. That's my blue time series versus the GAT anomaly. You know, mainstream argument is that when the Earth energy imbalance is positive, it's because of the CO2 greenhouse effect is rising. So the trapping of heat in the Earth's lower atmosphere is why we have an energy imbalance. That's what they're saying. The data I'm showing is no, it's because ASR is positive, larger than OLR. You're seeing the Earth energy balance is prevailing positive. And in this time series of the last 24 years, you really see that from 2012 to 2014, it's been consistently positive. And it's because that's the period where ASR is rising faster than OLR. You don't see like if you look around 2008, you see the Earth energy imbalance goes positive there, big spike around 2008, 2009. But the GAT anomaly drops. It goes into negative anomaly territory at the La Niña state. So the argument that is made, I find, has little support when you look at data like this. The argument that the Earth's global average air temperature is a function of EEI is not supported. When you look at, you compare these two time series, the R squared is it's embarrassingly low. There's no relationship. You cannot look at this and make that statement that there's energy imbalance drives the rise in drives the changes in the global average air temperature. There's no support for that. I think Rodney McInnes has been on your So he showed me a plot that I really like. This one here. He just looked at he plotted it slightly differently, but this is the EEI as a function of the seasonal cycle. Seasonal cycle meaning the transit of the Earth around the sun. That's all it is. It's just the difference between the global average absorbed solar radiation minus the global average OLR. And as you go from year to year, month to month, the one thing that is so abundantly clear is A, orbital dynamics is first order in determining changes in the Earth's energy imbalance. B, the second, the Earth is almost never in a state where its energy is in balance. The energy coming in versus energy going out. It's almost never in balance. And there's something very different about the southern hemisphere versus the northern hemisphere. When the sun is over the northern hemisphere, it's the EEI tends to be positive, and when it's predominantly over the southern hemisphere, it tends to be negative. It's a function of clouds largely, and the relative landmass versus relative oceans. So, whenever in doubt, I say this time and again, John, is when I'm talking with people about climate science, is don't start your studies about climate science without first seeking to understand the basics, which is the seasonal cycle, orbital dynamics. If you want to understand climate, you got to start with this. Put everything in perspective. Next slide. So in conclusion for this part, you'll see here is just the summarization of everything I've said, right? Walker circulation dynamics prevails. It dominates what we see when we're looking at a global average OLR. The data I'm showing shows like the GAT anomaly measured by satellites shows that it follows changes in OLR, which the literature is very clear. The Pacific warm pool is the strongest greenhouse effect for outgoing long wave radiation. And the fact that we see the trade winds correlated with GAT and OLR shows us that Walker circulation that is statistically dominating the global average change in GAT and OLR. So in other words, something purely natural is driving climate change. And I think I'm not going to read word for word all the other stuff there, because that to me is the most important take-home message here. There's not one greenhouse gas effect. There's two. And the one that is completely ignored is the one that dominates global average changes in temperature and global average changes in outgoing heat, at least according to these data sets that I'm showing you now. There's probably limitations to that. Like, I know like Ted Nikolov, I think Ned Nikolov, when he did his recent amazing piece of work, he used all of the air temperature time series, and he created a temperature time series that's an average of RSS, UAH, et cetera, so no one can say, well, it's just one, you're correlating changes in planetary albedo to just one change in air temperature. But I'm not an academic, I'm a rancher. I'll leave this for other people to work on. I haven't yet to see, Tom, I've yet to see a single study that's showing exactly what I showed here today. So if I can impress anybody who listens to your channel and who's in academia to do something better with this idea and these data sets that I have, awesome. That's then mission accomplished as far as I'm concerned. I've focused up to this point largely on the Pacific. I've focused as well on, in terms of data, on interannual change of 12-month rolling averages. Well, now start looking at what the broader literature has to say, with the focus on the multidecadal changes in clouds, multidecadal changes in absorbed solar radiation, sunshine hours across the northern hemisphere. Next slide. Well, here's one that I produced using UK Met Office data. They've got some of the best records on planet Earth in terms of sunshine hours as a function of season, going all the way back to the early 20th century. I also, so you hear the red, yellow, orange, whatever color that is. My apologies. The y-axis is normalized to 1914. Okay, and then I subtract. So it's unitless because I've done that normalization. I've divided the 1914 values by January 1st, 1914. And so it increases from there, from at 1 all the way up to basically the present. So it increased from about 1 to about 1.35. So about 35% sunshine hours during the winter and spring season over UK has increased since 1914. No surprise to people who are familiar with this topic, the undetrended Atlantic multidecadal sea surface temperature, which is just a region westward of the UK, shows the same temperature trend, where sunshine hours, which just for those who are familiar with the term, sunshine hours is the number of hours in a day, month, or year where the radiation exceeds 120 watts per square meter, right? So if sunshine hours is increasing, that means you're seeing less clouds. And sunshine, the surface radiation incoming from the sun, is you got more sunshine, less clouds, less shadow, right? So there's a very distinct correlation between these two time series. Next slide. This study is 2023. They did much the same thing. Here they use sunshine hours, the right-hand plot, sun duration, or SD, versus the AMO, right? Sunshine hours, in this case, I believe, is over Central Europe. So not just UK, but the whole Europe region. And that there they show the same correlation. What I found really interesting about this study as well is that the AMOC, or the North Atlantic Thermal Halide Transport, also shows the same temporal relationship, according to this study. Now, you'll go to one study to the next, and the AMOC, or the regional thermal halide heat transport rate varies. It's all over the place. But according to this method, this study, they shows the same. It's logical in my mind they would, because the thermal halide is a function of deep water formation, or dense, the rate by which dense, cool water sinks to the bottom of the ocean in the subpolar North Atlantic. So as cloud cover decreases, the sunshine hours decrease from the Atlantic tropics all the way up to the subpolar latitudes of the North Atlantic. As cloud cover decreases, you get more evaporation. As you get more evaporation, the salinity of the water increases. And so a higher saline water at cold temperatures in the subpolar region is going to sink faster. And so it would make sense that you would see a correlation between these three variables. So that's another study. Can move on. Here's a more recent study plot for all of Europe, and this is just from the recent satellite era, right? So the previous data I was showing was like station data, local station data, showing they've got a station where they got a sensor and shows you sunshine hours at that location. You can make the averages over lunar stations. That's how they got the long-term record. But over the modern era of satellites, we've been able to get the same, better data, more geographically coherent across the entire European region. So the top plot on the left-hand side is the cloud anomaly over land. And then the one below is just the associated sunshine duration anomalies over European land. And no surprise, as clouds go down. You've seen this in the last couple of decades. This is, arguably what people will say who are of the anthropogenic-centric view of climate. They will say this, they will focus on this data set, and they'll say this is because of increasing emission standards have reduced in fewer aerosols, and thus we see less cloud formation over Europe. Well, that's a perfect argument. It's very true. Anthropogenic aerosols do decrease as you emit less nitrogen and sulfur oxides into the atmosphere or pump out soot, right? So, but that argument ignores the longer-term station data, which shows you saw the same large rise in sunshine duration and sea surface temperatures during the first few decades of this is station data. Yeah, this particular time series, it starts in like 1935. UK Met shows it better, goes back to 1914. We see brightening during the first part of the 20th century when you saw the greatest rate of increase in industrialization in Europe, where we had almost no emissions control technologies, right? No scrubbers. So we see brightening, dimming, brightening. The argument that emission standards in the late 20th century was responsible solely for these changes, ignores the same effect at the beginning part of this century where there was no emission controls. So the same data, I really like this work that Martin Wild he's got some of the best papers on this topic. By the way, Martin Wild is very much of the anthropogenic centric view of this topic. He argues that humans caused the dimming from the 1950s to the 1990 region, and likewise it caused the brightening that followed. He's not a naturalist, but so there's different opinions, there's different arguments. The monthly average data that I want to show here is really interesting. It shows both station data and satellites show that where we see the most sunshine hour increase is during the late winter and spring region. And you saw that, I showed that on my earlier plot. The UK Met data was specific to the winter spring region. So there's something going on there with clouds that is very much localized in that time of the year that doesn't show up in the latter part of the year. So that's when the northern hemisphere is seeing the sun return, right? There's something going on with the response of clouds. In my naturalist perspective, that's where we need to be looking, is what physical processes are changing as we move through this from the spring equinox towards the summer solstice. There's something orbitally atmospheric happening there that we do not see when the reverse happens and the sun moves back to the southern hemisphere summer. Here's data from the other side of the world. You can't be entirely European Western centric. We got a great time series from Japan going all the way back to 1890. So on the opposite side of the world, in a region that did not industrialize the same as Europe, arguably, it shows that from 1890 to like 1910, sunshine hours decreased slightly, and then increased to 1940, and then decreased to 1980, and then increased into the 2000s. And then, no surprise, the temperature anomaly over China shows the same. So ASR is a very important factor in annual average and 5-year average data, longer term data. We're seeing very strong regional correlation between these two things. Next slide. Here's Augustine et al. 2022. This study is, I would argue, is a school of thought that I tend to prescribe to, which is the naturalist perspective on these changes in cloud forcing. This author is arguing more from a naturalist perspective. This is something fundamental. Humans may be influencing it, but it's not driven by us, first order. We're a lower order effect. So what they've done here is he's got these, you see the colored lines going up and down for like the early 20th century. The colored lines are just European, American, Japanese, Chinese stations showing this dimming, brightening effect with clouds versus the inversion PDO index. We're used to the Pacific decadal oscillation being oriented in the opposite form to this, but the author is bringing it back to the Pacific, seeming to be acting as the epicenter of these globally propagated effect. The starting point of my presentations was focusing on an interannual rate of change, the frequency of ENSO, and seeing the relationship with clouds. Most literature speaks very clearly that there are global teleconnections from the Pacific tropics out into higher latitudes. This argument here from this authors is along those lines. There seems to be a relationship there. So same study. This here is just the authors reminding the reader that anthropogenic aerosols don't always correlate positively with the observed changes in absorbed solar radiation, absorbed surface radiation, right? So the black, this is for surface station data, and it's an anomaly plot for the United States from 1995 all the way up to 2020. Notice the black line from 1995 to like 2011, 12. There is the black is going up, and the red, now the red is the U.S. aerosol optical depth. And the author is showing this that, well, during the first parting this, you're seeing that, yeah, it looks like there's an expected relationship as human aerosols are decreasing from 1990s up to the first decade of 2000s. As the human aerosol optical depth is decreasing, well, there's more sunshine. Well, that trend suddenly switched around 2010. Well, now over the United States, the author is reporting a negative, a dimming effect, but there's still a downward trending human aerosol optical depth. So, it's correlation doesn't necessarily always mean causation. That's just the author is just saying, hey, it's not as clear cut as people like to think it is. We don't know how much is natural or human. If you were probably look at studies where they're focusing, Tom, on say like the South China Sea or the Sea of Japan, you probably find some very strong human influence, right? Because say, for example, there's so much coal use, coal burning going on in that region of the world. It's very different from say over Nevada or over other parts of the world where there isn't a lot of human aerosols being released into the atmosphere. So global averages, again, limited. You need to always be focused on regional and think. I think this is getting pretty much it. Is that this last slide, Carl?
That is number 32 of 32, yeah. And then I did put a link to your Substack in the show description. Is that the best way for people to reach out to you later? Is like a comment through Substack or?
Yeah, a lot of the stuff that you just saw there, Tom, is content that I've written on in the last few months in my Substack. So by all means, that's the best place to reach me, especially since LinkedIn has a tendency of deplatforming people when they say the wrong thing.
All right. And actually, one other question would be, do you have any ideas what might happen in the next 5 or 10 years based on stuff that you've seen? Do you think that the dimming and the brightening will keep going in cycles and see some cooling possibly?
Okay. There's, as well as I, if not better, that lots of really smart people are trying to understand clouds. I'm not one of them. I'm not one of the smart people. I tried to read what they're doing, and I'm trying to make sense of what they're saying. The Svenmark idea, that model of the galactic cosmic radiation causing cloud nucleation, it's definitely got a really good base. There's some data that really supports it, and then there's a whole bunch of other data that says it doesn't answer enough questions, right? It's there's I don't have the data in this. Maybe it's another presentation another day, but there is the Schwab cycle influences the galactic cosmic radiation, right? It's the magnetosphere. The sun's big magnetic field is what modulates that. We see there's data out there that shows regionally certain cloud formations show a positive correlation with the GCR intensity modulated at the frequency of the Schwab cycle. And then you looked at other regions of the world, it's got a negative correlation. Completely opposite. So I think the most important thing that people have to keep in mind when they're reading or listening to people talk about their model, their hypothesis, always be wary of global average, global generalizations, because the global average, as I've shown in my presentation today, is dominant. It can be often dominated by regional dynamics. So regional atmospheric circulation patterns, like Walker circulation, for example, is we always have to bear that in mind, that we're not misinterpreting. So the answer is no. I don't have a long-term looking glass. I know there's people out there who tend to think that the sun's magnetic field is to go through a major dimming effect, a calming effect, quietening effect in the next decade or two. The interdecadal Pacific Oscillation is clearly a part of these processes on land. It seems to be correlated with planetary waves that are propagating between the ocean and land. That's another thing that some people are realizing or trying to understand. But the negative IPO state has been going on while the AMO's been in a positive. And those, I think if the AMO goes into a negative state while the Pacific is in a decadal cooling, that's where go buy natural gas producing company stock. Right. I think the AMO has been holding up the temperature of the higher latitudes of the northern hemisphere, which is where most humans live. And thank God for it, because winter sucks, especially when you get winters like that photo I showed, Tom, from 1949 in southern Alberta. That was when the AMO was negative. And as well the Pacific, particularly the PDO, the northern arm of the IPO, was in a deep negative state as well. And those two things are going in the same direction. That's when you get those really the polar vortex really drops during the wintertime into the southern latitudes. So you lose orange crops in Florida, right? So how that relates to the sun, though, I don't think anybody understands. Like, what's the name of that Russian scientist that is in New Zealand, done a lot of work on making predictions on the sun, is Dynamo?
Yeah, you're not talking about Valentina Zarkova, right? You're talking about another Russian?
Valentina Zarkova, yeah.
Okay.
Yeah, her model suggests that their sun is imminently approaching a quieting phase, right?
I think so, yeah. And another person who's going to talk about this on my podcast very soon is David Dilley. He thinks there's big-time cooling coming based on geomagnetic changes. So, yeah.
Well, I hope he's wrong. Put it that way.
Yeah.
There's a lot of people who are trying to predict what the AMO is going to do, right? And all they can do is model. But then models in the AMO and AMOC, they're like a dime a dozen. It's like pick one that you like.
But it just can't stay positive forever, right? Doesn't it have to go negative at some point?
Well, yeah, it's I think that we only have good data over the last 100+ years, right? All data prior to like the end of the 19th century is such poor quality that we've only just in the last 30 years discovered that multidecadal variability in sea surface temperature data for the North Atlantic, right? Not that timescale is showing up on so many indices: clouds, sunshine hours, sea surface temperatures, air temperatures, glaciers. But we have no data prior. So the only data we've got is it's been data smoothed so much using low pass filters that we can't see that harmonic. We can't see that 60, 70-year harmonic. And all we see is the longer term changes, which indeed are solar driven. Like that, there's no doubt about it. Radionuclide data geochemically shows that the planet warms when the sun's activity increases. When GCRs into the Earth's biosphere and the surface environment increases, and those radionuclides are being created, like beryllium, like carbon-14, when those concentrations are going down because the sun's magnetic field is increasing, the Earth warms. We know that. There's no doubt about that. And conversely, when the trends go in reverse, it's just, I think what it comes down to is people like other people are working on trying to come up with a high resolution model, like a model with better temporal resolution, so we can look at multidecadal instead of just centennial and millennial trends. But we don't got enough hindcasting data out there to really properly calibrate our results. Does that sound about right to you?
Yeah, it does sound right. And yeah, of course, you understand it way better than I do. But I do love the fact that you you showed us so much data here. I wanted to say that I am putting your slides up on my Substack so people can take a close look at all that work of yours. And I would love to have you on again. It sounds like, looking at your Substack, you got a lot of stuff going on climate-wise.
Yeah, I try to, but my subscribers, Tom, really like my climate focus. The analytics always are the best when I do climate stuff. But I'm not a climatologist. My formal background is environmental sciences. My formal background is in energy conversion technology. And I used to be an oil sands scientist and environmental scientist. So I really like energy topics. I really love geopolitics. And today, the climate science, energy science, geopolitics, they're all the same. And as far as I'm concerned, if you want to understand why money is being spent on pumping human-centric explanations for planet Earth's changes, you got to look at geopolitics and energy.
100%. I agree.
That's what my Substack does. That's what my Substack does. Talk about more and more here. So.
All right. josephfournier.substack.com. I encourage people to head out there. I will let you go, but thank you very much, and we'll talk to you next time.
Thank you very much, Tom.